Hi everyone. In this lecture, we will see this problem. Uh, if you're supposed to look into this slide, here they have given a steam at 70 bar and 450 degrees centigrade supplied to a steam turbine. After expanding to 25 bar in high pressure state. That means at this stage we have a one turbine is there. That turbine is called as a high pressure turbine. It is reheated to 420 degrees centigrade at this constant pressure. Next, it is expanded in the intermediate pressure stages to an appropriate minimum pressure such that part of steam blade at this pressure heats the feed pump to a temperature of 180 degrees centigrade. The remaining steam expands from this pressure to a condenser pressure of 0.07 bar in the low pressure stage. The isentropic efficiency of high pressure stage is 78.5, as well as while that of the intermediate and low pressure stage is 83% each. For the above data, determine the minimum pressure at which bleeding is necessary, the quantity of steam blend per kg of flow at turbine inlet, and also you have to find the cycle efficiency. Here in the problem that they given as neglect the pump work. That means you need not to calculate the pump work in this problem. Here, what he has given is a steam at a 70 bar and having the 450 degrees centigrade is supplied to a steam turbine initially. Initially, sorry, initially we have a pressure of 70 bar as well as the temperature having the 450 degrees centigrade. After expanding, which is having, for suppose there is a 70 bar of pressure initial and as well as the temperature is the 450 degrees centigrade. After the expansion is happen in the high pressure stage, that means initially we have a high pressure turbine. In that high pressure turbine, we have the expansion. Uh, the 70 bar of pressure of steam is expanded up to 25 bar in the high pressure turbine. Then it is reheated. If you look into this one, then it is reheated to 420 degrees centigrade at this constant pressure only. The reheating process is happen up to 420 degrees centigrade at this particular constant pressure. Then what is happen? It is expanded in the intermediate pressure stage. That means there is a one intermediate pressure stage is there. That is approximately minimum pressure such that some part of steam blade is taken to the feed heater. That is a regeneration process. That part of steam heat is taken at a 180 degrees centigrade. You're supposed to read this one. Some part of steam is sent to the feed water heater at a temperature of 180 degrees centigrade or 180 degrees centigrade. The remaining steam is then expanded from this pressure at a condenser pressure of 0.707 bar. That means they have a three turbines is induced in this cycle. First one is the high pressure stage. Second is the intermediate turbine is there. Then after we having the remaining steam is expanded from this pressure. That means there is a low pressure stage is also there. After the expansion, all the expansions which is happened by the three turbines, the pressure becomes to the 0.07 bar in the low pressure stage. Here in this problem, he has given the isentropic efficiencies also for a particular turbine. In the when it comes to the high pressure turbine, the isentropic efficiency is 78.5%. And when it comes to the low pressure and in low pressure turbine as well as the intermediate pressure turbine, we have a 83% of isentropic efficiency is there. For this, we have to calculate what is the minimum pressure at a steam blade is necessary. That means at a 180 degrees, you are taking the steam blade to the heater. For that, you have to find what is the pressure, minimum pressure for taking that steam blade at a 180 degrees centigrade. Then the quantity of steam blade per a kg of flow at a turbine inlet. That means how much amount of steam, the quantity of steam is taken from the turbine inlet. You have to calculate that, and also you have to find the cycle efficiency here. Just look into this schematic diagram of this problem. What is happening initially? Forget about the zipper heater, all these things. What is happening here? Initially, at the first state, we have a 70 bar and 450 degrees centigrade. Then this is comes to the high pressure turbine. Then it is expanded. Uh, After the expansion, the pressure becomes to 25 bar. Uh, Here, at the second state, we have a pressure of 25 bar. 25 bar. And at this pressure only, the expansion process is happening. At this pressure only, at this pressure only, the reheating process is happening. In this problem, you may study that it is reheated at a 420 degrees at constant pressure. That means after the expansion from 70 bar to 25 bar, the fluid is just reheating. By taking the fluid bring back to the boiler. Here the indication is not sufficient, but the fluid is just bring back to the boiler. Then, or you may utilize the energy where you have to uh, reheating. Utilize the energy for reheating purpose only. Here, at the 25 bar only, the fluid is just reheated. By that reheating, the temperature of the fluid is increases up to 420 degrees centigrade. This is sent to the intermediate turbine, intermediate stage or intermediate turbine. Here they have three stages in the turbine. This is the high pressure. This is the intermediate one, and this one is the low pressure. After the expansion happened, 25 bar to at 25 initially at a 25 and 220 bar. Then after not completing expansion, we are taking it a steam blade at the fourth state. We are just taking a steam blade at a fourth state, and it is sent to the uh, feed water heater. Open. This one is taken as an open type. Then the remaining fluid, which is participated in some expansion, then after it go into the low pressure stage. In the low pressure stage, this fluid is just what is that called compressed expanded up to 0.07 bar. This fluid is just expanded up to 0.07 bar only. Then this is sent to the condenser where the constant pressure heat rejection is happen. Then this fluid is sent to the feed water heater through the pump. In the pump, what is happening? Isentropic compression is happening. Due to that, the fluid pressure is increasing. Then after this fluid is just only comes to the feed water heater, where the exchange of heat between the M1, you may take it as M1, not M1, and here also we have M1. Here also we have here the steam taken from the intermediate turbine as well as the fluid which is coming, the water which is coming from the pump. These two are exchanging the heat with each other. After some maintaining the equilibrium state only, then this fluid is bring back to the boiler by compressing the fluid through the pump. This is all about our problem. In this problem, initially we have a temperature and pressure. 450 degrees of temperature is there and 70 bar of pressure is there. Then after the expansion, we have it pressure of 25 bar, as well as after complete expansion of the what is this called? After complete expansion happening in the three stages, the pressure becomes to 0.07 bar. Okay. For suppose for this one, I have to find what first one I have to find. First one I have to find is the minimum pressure and quantity of steam and as well as the cycle efficiency. This is your TS diagram indication. Here at this position we have a state 1, and from state 1 to 2 this is the actual ideal one. Suppose look this one. In the problem we have here they have given the isentropic efficiency of a turbine also. By that the actual turbine work is different from the theoretical one. If you look into this diagram, the 1 to 2 is a theoretical one, expansion process, turbine expansion, isentropic expansion happens in the theoretical one. When you consider 1 to 2 dash, 1 to 2 dash, sorry, 1 to 2 dash, it is the actual one. Actual turbine work, turbine in process, isentropic expansion, expansion process, which is happens in the actual manner. Then what is happening from 2 to 3? There is a reheating process happens between this uh, fluid to fluid within the fluid. Sorry, within the fluid. From after at the 3 to 4, there is an intermediate pressure. Intermediate turbine is there. By that, some expansion is happens at this particular position. Then, if you supposed to look this one 3 to 4 dash, this is the actual one. Actual expansion happens in the intermediate pressure. When it when you say 3 to 4, this is the ideal work done by the turbine. After at the fourth state, we have taken the some amount of steam blade here. Then this fluid at a 4 dash to 5, we have a what is that called isentropic expansion, theoretical expansion. Then the 4 dash to 5 dash, the turbine, low pressure turbine follows the actual process, which is taken as the actual expansion. Then the condensation, pumping uh, are common. And when you look this one, 4 dash to 8 as well as the 7 to 8. Here, from the 4 dash to 8 and 7 to 8 are the simultaneous process which is happens in the open feed water heat. These two, these two are done at the same time. By that, there is a heat exchanging which takes place between the two fluids. Then after, what is happening? After some attaining the equilibrium state only, this is sent to the pump sent to the boiler through the pump. Here, the 8 to 9 process indicates a pumping process or isentropic compression. This is all about your what is this called? Yeah, all about your problem description. First of all, you have to find the minimum pressure at which steam blade is necessary. That indicates uh, what is the minimum pressure required to uh, steam blade is taken to the open heat. That is the here here is the first question. For finding that one, we have to take what is the temperature at 180 degrees centigrade only the steam blade is taken to the open heat. Just you have to go to the steam tables now. Wait a second. Keep this one. Wait a second. Yeah. If you look this one, uh, at 180 degrees centigrade, I have to take the saturation pressure. Before going to that, I have given an explanation for this. I have to give. Uh, if you look this one, what is the minimum pressure? You have to calculate for the steam blade. If you look this one, what is happening? At this particular condition, I have to take at 180 degrees centigrade. I am taking the steam blade. At this condition, the pressure is the saturated pressure. Then at this constant pressure only, we are taking the heat is exchanging. If you supposed to look this 4 to 8 process and 7 to 8 process, these are done at the same time, which is happens in the open heater. If you look this schematic diagram from 4 to 8 as well as the 7 to 8, these are done at the same time, which is happened in the open feed or feed water heater. Here at this position, we have a temperature of 180 degrees centigrade. At the fourth state, we have a temperature of 180 degrees centigrade. degrees centigrade. At this temperature, we are taking the steam blade to the open heat. At this pressure only, at this what is the pressure which is having in the fluid? Only at a constant pressure only where the heat exchanging is happening. For that, what initially the pressure is having the inlet at the fourth state is having the eighth state also. For this, at this particular pressure only we are taking the steam. For that, I have to go at 180 degrees centigrade. What is the pressure I have to take? Here, I am just going to the steam tables. I'm just going to the steam tables here. For that, I am going to the temperature based tables. Why? Because I am know the temperature only. These are the temperatures, and I am going to the 180 degrees centigrade. At 180 degrees centigrade, I have a pressure of 1.00028. That gives you a 10.028 bar. At a 180 degrees centigrade, if you look this one, at a 180 degrees centigrade, we have a pressure of 1.0028 megapascals. Here the pressure is in the megapascals. If you convert this pressure megapascal into the bar, then the bar should be 10.028. That may be approximately 10 bars. I am taking that as a 10 bar. Here I am taking the value here. For this one, first you have to first condition is what is the pressure that the steam bleed is taken. That is equal to Psat, P saturated, saturated pressure. That is equal to your P4 as well as the P8. P4. That is equal to 10 bar. That is equal to 10 bar. Here in the TS diagram, he already gives that. The 10 bar is the pressure where the steam bleed is taken. Then after you have to find the quantity of steam bleed per flow of at a what is how much amount of steam bleed you are taken, how much quantity of the amount of steam bleed you are taken from the turbine is you have to calculate. For this, if you suppose for this one you have to apply a energy balance equation at the open heat. For this, they have two inlets and outlets. What is the inlet energy is coming to the open heater and outlet that is equal to the outlet energy. That much amount of energy is leaving from that open heater. For finding this mass quantity of steam or taken from the intermediate turbine, for calculating this, you have to know what is the enthalpies for that particular position. Before going to that one, I'm just finding the enthalpies from the HS diagram. I'm just taking the enthalpies of at a particular state 1, state 2, and state 3, as well as the 4, and all these things. I'm just noting it down. Okay, I'm first taking the H1, H2, H3, H4. Why? Because I am knowing the temperatures as well as the pressures at that particular condition. Okay, here in the TS diagram, there is one mistake is there. The temperature here is a 450 degrees centigrade. At the first state, we have a temperature of 450 degrees centigrade. This is mistakenly taken. The exact value here in the problem is the 450 degrees centigrade. Okay. For marking the H1, H2, H3 as well as the H4, I'm just going to find the. I'm just taking from the Moeller chart. This is a Moeller chart where I have to, at first condition, I have a 70 bar of a pressure. This is a 50, 60, 70, 50 to 100. I may have a 70 bar at this particular condition. And I have a temperature of 450 degrees centigrade. If suppose the 50, this is the 50 line, and this is the 75 line, and we have a 100 line here. This is the where nearly 75 line. That is the intermediate line passing between the two lines. This is a 75 bar line. Suppose if you look this one is the 50 and this one is the 100. This is the 75 line. And I think you already aware of this HS diagram. In this HS diagram, these red lines indicate that the dryness fraction lines, and the blue lines, which is having linear ones, is curvilinear ones, is indicated as a constant pressure lines, and the green lines is indicated as a constant temperature lines. Okay, here in this axis we have a enthalpy. Here in the horizontal axis we have a entropy. For finding the H1 and the HS diagram, first of all I have to mark the what is the enthalpy at that particular conditions. And 50 to 70, I have a position at the 70 position. I have a 70 bar line. I have a mark on this. The line may follows this one. And at this condition, we have a 450 degrees centigrade. This is the 450 degrees centigrade line. This green line indicates the 450 degrees centigrade line. And we have a 70 bar line at this position. And these two are met at this position. So taken this carefully. These two are met at this condition. At this position, I have the H1 value at a 450 degree centigrade and 70 bar. This is the 450 degree centigrade line. And this is the 450. This is the position where I got the first position. At a 450 degrees, 450 degrees centigrade and 70 bar, I have a first position. If you take the enthalpy values on the vertical axis, this may hit at this position. At this position, we have the enthalpy that is approximately equal to, here the H1 is equal to 3000. If you take a look on this is the 3000 line, 3100 to 200, and this is the 3300 line. It may be approximately have the in between the 2080 to 90. That you gives the value of the intermediate position of these two values. I am taking the 3285. 3285. Usually, the units of the enthalpy is kilojoules per kg. You have to take the enthalpy units of the kilojoules per kg. For this, the first point is 1. Then, after going to the second position, the expansion, which happens in the high pressure stage, is after the expansion, we have the pressure of 25 bar on. For this, we are only knowing the pressure only. I don't know the second position, the temperature. But I in 1 to 2 process, the actual the critical expansion happens in the isentropic manner. Here in the x-axis, if you look this HS diagram, then the x-axis they have a entropy lines on there. Entropy indication is there. If suppose if you draw a straight line that is equals to the straight line at this position, at the 6.5 position, I have a Entropy is the constant because there is no change in this line. Here in the 1 to 2 process, critical expansion process, they have a expansion process is follows the isentropic expansion. The theoretical expansion is follows the isentropic expansion. If you draw a straight line for this particular first position to the horizontal horizontal axis, that will give you the constant enthalpy, constant entropy. I'm just drawing the straight line here. Sorry. You just draw a straight line. At this straight line, on this line, and at a 25 bar, this is the 20, 30, 20, 30, 40, 50 line. Oh, I think 4, 10, 20. This is the 20 bar line, and this is the 50 bar line. That means 60, 80, 100. Sorry, this is an 80 line, 80 bar line. And at approximately at this position only, we have it 70 bar line. Not a problem. And at this condition, we have a 20 bar line and 50 bar line is there. 30, 40. Uh, the intermediate position of these, the middle position of these two lines gives you a 25 bar. At this condition, we have a 25 bar line at this position. The 25 bar line is starting at this position. And the path of this line is follows like this. If you're supposed to look this one, if you suppose if this line is follows like this, and this is touches at this position. If you take this is a 20 bar line and this is the 30 bar line. The intermediate position, the middle position of this one is gives you a 20 bar line. If you extend this line up to this point, where the line touches the 1 to this green line, that will gives you your, what is that called, that will gives you your second position. That means after at 25 bar where the expansion is end, at this position I have to take the value of h2. I think this is yeah, at this condition. I'm just taking the, at this condition we have a second state. For this I have to take the enthalpy. That is equal to approximately equal to h2 is equal to 29. Why? Because if you look this enthalpy line, there is a 2500, 600, 700, 800, 900. That means 2980. The enthalpy value is 2980. What is the units here? Kilojoules per kg. The enthalpy value, the enthalpy is usually, the units for the enthalpy is taken as kilojoules per kg. Okay. Here, the first position and second position is out. Then, at this constant pressure only, we are reheated up to 430 degrees centigrade. At this constant pressure only, we are just heating that fluid up to, what is the, up to the what is that called? 430 degrees centigrade. I think 430 or 420. 420 degrees centigrade. Yeah, 420 degrees centigrade. At this constant pressure only, that means you have to follow the 25 line, and the 420 degrees centigrade is my lies at this position. At this position, maybe at this position. If you saw a cursor on this, if you look into this cursor one, at this constant pressure only, we have a third state. This is the position of third state. There is a 400 and there is a 50 divisions in this intermediate 50 divisions are there. That's why I'm taking the 20 at this position. Yeah, at this position only I got the point. Just wait a second. I mark the position of the third state. At this position, we have a state 3. At this, it is very nearer to this guy. If you take a particular note on this, the H3 is equal to H3 is equal to 3280. The H1 and H2 always are very nearer to each other. The units for the enthalpy is always taken as a kilojoules per kg. You may take it as a kilojoules per kg. Then you have to mark the fourth position. How you have to mark the fourth position? The 3 to 4 process is a isentropic expansion process. Isentropic expansion process. For that, we have know the 10 bar of a pressure. I think 10 bar of a pressure is there. Yeah, a 10 bar pressure only. I am taking the steam plate. I'm already calculating the pressure here. At the fourth state, we have a pressure of 10 bar from the steam tables. For this, at a 10 bar and a straight line. Yeah. If you're supposed to draw a straight line here, that will gives you isentropic process on this enthalpy chart. I'm just drawing the straight line here. Sorry. Wait a second. On this position, just draw a straight line and mark the fourth state at a pressure of 10 bar. This is the 10 bar line. The 10 bar line is just touching this line at this position. If you mark on this, for this we already know the temperature also. Steam blade. So the steam blade is taken at a 180 degrees centigrade. Yeah, 180 degrees centigrade. Then what is happening at a 10 bar? This line may touch at this position. That will gives before happening the expansion. The steam blade is taken at a 180 degrees centigrade, but the expansion is somewhat have a higher temperature than the taken of the steam blade. If you're supposed to look this one at a 10 bar, this is the 10 bar line, and this hits at this position. At this position, the two lines are met together, where the temperature is approximately equal to the 270 degrees centigrade. But you are taking the steam at a 180 degrees centigrade. That will differ from this position to that position. Just you may mark whatever the position you got. At this position, I got the fourth state of the fluid. This is the 10 bar line, and at this state, just wait, I'm changing the color. Yeah, this is the 10 bar line, and these two are met at this position. At this position, these 2 points are met together. The enthalpy at the state 4 is taken at this condition. If you look this one, that is the H4 is equal to 3030 kilojoules per kg. 3030 kilojoules per kg. We are already taken the H1 as well as the H2 as well as the H3 and H4 from the steam tables. No, sorry, from the enthalpy diagram. For this, first of all, I am going to the TS diagram. If you look this TS diagram, they have a two processes happens in the turbine. One is a theoretical one and the actual one. Here in the problem, they have given the isentropic efficiency of a turbines. For that, I have to calculate the what is the actual enthalpy at that particular conditions. I have to calculate H2 dash as well as the H4 dash and H5 dash. H5 as well as the H2 dashes. I have to find H5 as well as the H5 dash also. If you are taken the H5, for that, first of all, I am calculating the H2 dash. For calculating the H2 dash, here, the isentropic efficiency of a turbine, isentropic efficiency of a turbine uh, for high pressure stage, that is the equation for that is actual that is equal to actual work done. Isentropic efficiency of a turbine is equal to actual work done by the turbine by isentropic work done of a turbine. The isentropic efficiency of a turbine is taken as actual turbine work by the isentropic turbine work. For this, you have to write an equation. Here, the actual work done of a turbine is equal to H1 minus H2 dash by the ideal work done of a turbine is H1 minus H2. Sorry, this is the H. H1 minus H2. Here in the problem, they have given the efficiency of a turbine is the efficiency of a turbine, high pressure turbine is the 78.5. That is 0.785. The 0.785 is equal to 0.785 is equal to, here we know the H1 as well as the H2. The H1 is the 3285 kilojoules per kg and H2 is the 2980. Here the H1 is the 3, sorry. Here the H1 is a 3285, 3285 minus. I'm just taking the values in this equation. We don't know the H2, H2 dash. We don't know the H2 dash value. We have to find that one. And here the H1 is a 3285 minus the H2 is usually taken as a from the Euler chart is 2900. If you calculate this one, the H2 dash is equal to 3000 3045.6 kilojoules per kg. Kilojoules per kg. Okay. For this actual process, I am just calculating the H2 dash. The remaining terms here is the H4 dash as well as the H4 dash. First of all, I know the 3 and 4 process. That's why I am taking the H4 dash here. I'm just taking the value here. The efficiency of a turbine, sorry, which is taken as an intermediate pressure turbine. For isentropic efficiency of a intermediate pressure turbine. I'm just considering the intermediate pressure turbine. Here, the efficiency of a turbine work is usually taken as WT by the actual work done by the ideal work done. If suppose if you look this TS diagram, here the actual work done of a turbine during the 3 to 4 dash and the during the intermediate pressure, 3 to 4 dash is the actual work and 3 to 4 is the ideal isentropic work. Here the equation is the actual work done by the isentropic work done. That's why I'm writing the H3 minus H4 dash by H3 minus H4 dash by what is that called isentropic one? H3 minus H4. We know the value of efficiencies as well as the H3 efficiency of isentropic turbine in the intermediate pressure turbine and H3 H4. Here the H3 value is the 3280 and the H4 is the 3030. And the efficiency here I have to take it as 0.83. That means 83% of efficiency is there in the intermediate as well as the low pressure turbine. The 83% that may taken as 0.83. That 0.83 pressure efficiency of a turbine efficiency is there, and the H3 is the 3280 kilojoules per kg. We don't know the H4 dash. I have to find the H4 dash by here the H3 is 3280, which is taken from the Euler chart, minus What is the H4 here? The H4 is usually taken as 30. Usually taken from the boiler side, that is a 3030. If you calculate this one, wait a second, I'm calculating and tell you that what is the value got of the H4 dash. Now, the H4 dash is equal to H4 dash is equal to 3072.5. 3072.5 kilojoules per kg. Okay. Here I find the H1 as well as the H2. Just wait a second. For finding the H5, I need to know wait a second. Yeah. For finding fifth position, I only know the pressure of this substance. For this one, I have to know the saturation temperature at 0.05 bar, and I have for at 0.05 bar, and this one. Okay, I have the 0.05 bar of pressure. Then, if you supposed to look this one 4 to 4 dash 4 to 5, what is happening? A 4 to 5 is usually taken as a 4 dash to 5. Sorry, not 4 to 5. A 4 dash to 5 is usually taken as a isentropic expansion. If you look this one from 4 dash to 5, this is the isentropic expansion. I'm already calculating the 4 dash from this position to this position. I have to take the fifth condition. I'm again going to the Euler chart. Here I forgot to mention F4. At this particular pressure only, we have the enthalpy. Suppose for 4 dash I have a 3072 point. That means this is the 3000, right? 3072 point. What is that? That I have 3072.5. I have to mark the enthalpy here. 3000 and this is the 100. This is where we have the 3072.5. That means approximately at this position, at a 10 bar pressure. At this position, we have a 3072 bar of a bar. Actually, 3072.5 kilojoules per kg of enthalpy is there at this position. At this condition, only this is the fourth state. This is the 4 dash state. At this position only we have the 4 dash. Then we have to mark the fifth position at a constant entropy process. Why? Because the 4 dash to 5 is your constant expansion process, that is a isentropic expansion. For this you have to mark the enthalpy at the fifth state. For this I have draw a isentropic expansion process line. Okay, this may be your line. And the pressure at the end of the expansion is 0.07 bar. At the end of the expansion, which is happens in the low pressure turbine, is a 0.07 bar. For this, I have to take the value of enthalpy at the fifth state is at a 0.07 bar. That means I have a 0.05 bar line and 0.1 bar line. The intermediate position, the approximately this position, we have a 0.7 bar line. If you extend this one up to this line, up to this line, that will gives you the enthalpy at the fifth state. If you suppose this is the 0.0, if you suppose to look into this Nelson's diagram, this is the 0.05 bar line and this is the 0.1 bar pressure line. At this position, we have a 0.7 bar of a 0.07 bar of a line. If you extend this line up to this entropy, constant entropy process line, at this position, approximately, sorry, at this position, I have the fifth state. Just wait, I am just marking that line. At this state only, these 2 points are meshed together. I have to mark these 2 positions. For this, at this condition, I have a enthalpy at the fifth state. This is the 2000, 2100, 2200. It may approximately, sorry, at this condition. Not that condition. Not at that particular position. At this condition only, that line hits that position. For this is the point. This is the point where the fifth state of enthalpy is. Here the H5 is taken from the Euler chart is equal to 2210 kilojoules per kg. 2210. Usually the kilojoules per kg is the enthalpy. Just if you look this one, what is happening to this Euler chart? I am taking the enthalpies is at the first state we have a 450 degrees centigrade as well as the 70 bar line. That two terms are hit. Those two lines are met this position. I'm marking just this position at a. Um, Wait a second. At this condition, I have the enthalpy of this much, that is equal to 3285. And then I'm extending this line, extending from this point, I'm drawing a line in the vertical manner that gives the isentropic expansion, isentropic line. At the 25 bar pressure, I have the, wait a second. Okay, at the first position, I have the enthalpy of this much. If suppose I'm extending the line like this, if I am extending the line, if you suppose to look this green line, this line indicates that there is no change in the entropy. At this line only, I have a mark on the second state. Why? Because the 1 to 2 process is the isentropic process. At 25 bar, the 7 at 25 bar we have a second state. Second at 25 bar pressure only we have the second state. For that, in this line, E line law, where The 25 bar line is met at this position, at this line. I have to mark that position for finding the enthalpy at the second state. The 25 bar line may start at this position. If you extend this line to up to this vertical line, that will gives you a second state. For that, you have to take the enthalpy value. Then after, at this constant pressure only, we are reheating the fluid. If you're supposed to take the value at a 430 degrees centigrade, 420 degrees, sorry, 420 degrees centigrade at this particular pressure, that will gives you a third state. Then after, if you extend this line to fourth state, I may got the fourth state at the pressure of 10 bar. Then after, what is happening at this pressure only, we are just increasing its somewhat at this pressure only we have a 4 dash. Then this 4 dash, ఇక్కడ 4 dash నుంచి ఒక straight line గీస్తే that will indicate the isentropic expansion process, and at this process only we have a fifth state. At what pressure? At a 0.07 bar position. For this I am noting the all values here. I know the H5 value. For that expansion process I am writing it here. For this expansion process which is happens during the 4 dash to low pressure expansion, not the 4 dash or 4 dash anything, 5 dash anything. I'm writing the expansion equation, isentropic expansion equation or isentropic efficiency of a turbine for the low pressure states. I'm just writing an equation for a low pressure stage of a turbine. For that, the efficiency of a turbine, isentropic efficiency of a turbine is equal to, I'm already taking the equation in twice in this problem. That is equal to, wait a second. That is equal to actual work done by the turbine by isentropic work done by the turbine. That actual work done here, if you take this one, if you look into this diagram, the actual work done is done during the process of 4 dash to 5 dash. Then the theoretical one is taken as a from the 4 dash to 5. That means if you're supposed to write down an equation for the isentropic efficiency of a turbine, that is gives you the H4 dash minus H5 dash by H4 dash minus H5 minus H1. The H4 dash minus H5 dash gives you your actual work done by the turbine, and H4 dash minus H5, sorry, this is not a H4. Sorry, that is usually taken as a H5. That you see isentropic efficiency of a turbine. H1. We know already H5 and H4 dash. By that, I have to find an find H5 dash here. Here the efficiency is the 0.883. That means 83% of efficiency is there in the low pressure turbine. That is equal to, what is the H4 dash here? I am finding the H4 dash by this equation. That is equal to 3072.5. Sorry, 3072.5. 3072.5 minus, I don't know the H5 dash here. I have to find the H5 dash in this by this equation. By The H4 dash here is the 3070, 2.5, 25 or 5? Yeah, 5. 72.5 minus. Here I have the H5 value. The H5 is the 2210 kilojoules per kg. From this equation, I may got the H5 dash is H5 dash is equal to, just wait, I'm calculating. That is equal to 2356.6. What is the units here? The units for the enthalpy is taken as kilojoules per kg. Kilojoules per kg. I know the H1, H2, H3 as well as H4 and H4 dash and H5 dash. If suppose I want to draw a HS diagram here, that line may follows like this. Sorry. This is the representation of your cycle in the HS diagram. Here I have find the all enthalpies up to turbine work. In the problem, first of all, we have to find the quantity of steam. Then after, we have to find the efficiency of the cycle. For efficiency of the cycle, you may calculate the heat transfer also. For the first of all, wait a second. I'm just adding some slides here. Okay. For finding the steam first, amount of steam taken from the turbine outlet. At this condition, we are taking some amount of steam, M1 amount of steam to this condition, at this heater. Then after at the seventh state, we are returning the 1 minus M1 amount of mass to the feed water heater. These two are participated in the heat exchanging. Then after, it comes to the unit mass. If suppose I am writing the energy balance equation for this, H4 and H7 are the inlet conditions for the open heater, and H8 is the outlet condition for the open heater. I want to write an energy balance equation for now. The mass taken from the fourth state is the M1, and the inlet condition for the respective one is the H4 plus, and at the seventh condition also I am taking the, at the seventh position also I am taking the, what is that called? Raise. At the seventh position also I am taking the, I'm having one inlet. 4 and 7 are inlet and 8 is the outlet here. At this condition, I am taking the mass of, I have the mass of 1 minus M1 at the seventh state. M1 into H7 is equal to H8. 1 into H8. We don't know the enthalpies values of H7 and H8. For this, also I have to take the value of H8 as well as H7. If you're supposed to take a H8 value here, if you've taken the H8, that is usually as a saturated liquid at a pressure of 10 bar. At a 10 bar pressure, I have a what is this called? This is the saturated liquid. I'm just going to the steam tables. I'm taking the HF value at a 10 bar pressure. Just wait a second. I'm opening the steam tables. Here, at this condition, I'm only known the pressure here. For this, I'm going to the pressure based tables. I'm just going to the 10 bar. 10 bar is 1.01 megapascal. Yeah, these are the pressure based tables. In this, at 1 megapascals, these are the values. These are the values of water. These three covers the entropy and these three cover the enthalpy. If you take this one, 762.52 is the enthalpy of a fluid. If you take this one, 762.52, that is the enthalpy at a 10 bar of a pressure. HF, that is the liquid enthalpy pressure. I'm taking that value. Here, the H8. What is happening to this equation? Yeah, here the H8 is equal to, that is the saturated liquid. That's why I'm taking the saturated liquid as a at a 10 bar is equal to 762.6 kilojoules per kg. Also, I have to find the HF value. So H7. And also I'm taking the taken at a saturated liquid only. Why that has happened? Usually in the problem, it states that you have to neglect the pump work. You have to neglect the pump work here. For this, the H6 is and H7 is equal. For this condition, the H6 and H7 is equal. For this, you have to take the HF value at the sixth state is equal to the H7 value. That is at a 0.07 bar. I am just opening the steam tables again. At a 0.07 bar, I am going to the 0.07 bar of a pressure. For that, I have to take the value of HF. Yeah, 0.07 bar. That means 0.00007 megapascals. At this condition, these three are your entropy values, and these three are covers your enthalpy. When it comes to the HF value, that is equal to the 163.35. Why? Because here you have to neglect the pump work. For you have to neglect the pump work, there is a H6 is equal to H7. That means the enthalpy in the pump is usually taken as equal. For that, the H6 is equal to H7. Then the HF7 is equal to the HF6 value. Then at a pressure of 0.07 bar. Usually, here in this steam tables we have a megapascals only. For that, the 0.07 bar is in the megapascals is taken as a 0.007. At a 0.007 of a megapascals pressure, I have a HF value is equal to 163.35. 163.35. I'm again going to the presentation. Here, the H7 or HF7 or HF6 is equal to 163.35. 160. The units for the enthalpy is usually taken as kilojoules per kg. If suppose it is in a specific enthalpy. 163.35 kilojoules per kg. I know the for this equation I know the H4 value as well as the H7 and H8. I have to calculate the mass or quantity of mass taken from the turbine. I'm just incorporating the values in this equation. I don't know the M1 here. For H4, the H4 value is the 3030. The H4 value here is the 3030. Just substitute the values in this equation. The H4 is here is the 3030 plus 1 minus M1 into what is the H7 here? 163 point, sorry, 163.35. These are taken from the steam tables, sorry. 163.35 is equal to 762 point. The H8 value is here is the 762.6. If you solve this equation, the mass flow, the M1 is equal to, and just wait a second, I'm just calculating this one. Okay, that is equal to 0.206 kg. This much amount of mass is taken from the turbine, intermediate turbine. Then what is the remaining term? We are already calculating the quantity of steam as well as the minimum pressure. These two things are over. Then remaining one is the cycle efficiency. The cycle efficiency of a Rankine cycle or regenerative reheating combination Rankine cycle is equal to here W net by heat supply. What is the W net here? Just you have to neglect the pump work in this equation, in this problem. You may not consider the pump work here. The remaining work here is the WT only. WT only, the remaining. And what is the heat supplied here? They have a two heat interaction in this cycle. I'm just writing directing down directly. If you're supposed to look this diagram, the 9 to 1 process is one heat addition as well as the 2 to 3. They have a two heat interaction in this cycle. 9 to 1 as well as the 2 to 3. These two are heat addition processes in your cycle. If you're supposed to write an equation for this, where is this? 9 to 1, that means Q 9 to 1 plus Q 2 to 3. This is the equation. When you want to write a turbine efficiency, work done for a turbine, they have a three independent turbines are there. You're supposed to link this one. 1 to 2, there is a high pressure stage is there. Then after 3 to 4, we have a interaction 4 dash. 3 to 4, we have a interaction of a intermediate pressure. Then after 4 dash to 5 dash, we have a low pressure stage of interaction. Expansion is happening. They have three different processes of expansion is there. For that, I have to write down an equation. If you want to write down an equation for this 1 to 2 dash, that will gives the what is the mass here? Here the mass is 1 to 2. Sorry, 1 unit of mass is there during the process of 1 to 2. For this, I am writing the 1 into H1 minus H2 for the low pressure turbine work done. For intermediate pressure of a turbine, intermediate pressure turbine, the work done is equal to what is the mass here? Here also we have a unit mass is there. Supposed to look this one. We don't taking any mass out from the system up to fourth state. At the fourth state only we are taking the some amount of mass from the out of the turbine. At this condition also we have a unit mass and the work done is here is a H3 minus H4. H3 minus H4. Then the work done for a low pressure turbine is usually taken as here the mass is different from the two remaining expansion with the other expansion. Here the mass is 1 minus m1. Why? Because at the fourth stage we are taking some amount of bleed from the out of the turbine. The remaining mass is the 1 minus m1 into what is the enthalpy here is the h4 dash minus h5 dash minus h5 dash. If you sum up all these equations together, sorry, this you may take it as a h5 dash. H5 dash. So the sum of all equations, the low pressure turbine work and intermediate pressure turbine work as well as the low pressure turbine work together, then this gives you a WT. Here I am again writing the equation. The total work done by the cycle is equal to H1 minus H2. H1 minus H2 plus what is the again one? There is a H3 and H4 processes. And I am again writing H3 minus H4. Later we have a low pressure expansion having the process of 4 dash to 5 dash, that is equal to 1 minus m1 and minus m1 m1 into h4 dash minus h5 dash. Oh sorry, I forgot to mention here. In this cycle you have to take the actual work only. Don't take the ideal work done of the turbine. Here from 1 to 2 the expansion happens in the high pressure turbine is a critical expansion. The 1 to 2 process is the only actual expansion happen in the high pressure turbine. When it comes to the intermediate pressure, the process is the H3 to H4 dash. Don't take the values of critical ones here. Why? Because here already gives the actual efficiencies is there. We are already calculating the actual what enthalpies. For that, you have to take the actual enthalpies. For finding the efficiency of a cycle, you have to take the actual enthalpies only. This is all about our turbine work. Then by they have a two heat interactions. One is the Q9 to 1 as well as Q2 to 3. For this, I am writing the equation as Q1 H1 minus H9 for the Q9 to 1, as well as when it comes to the 2 to 3 process, the heat transfer is equal to H3 minus H2. This is all about your processes. Here we know all the enthalpies here except the H9. I have to know what is the enthalpy at the particular state 9. At this condition, I have to know the enthalpy. Here they have a condition. You have to neglect the pump work. That's why at the eighth position only, you have to take the enthalpy value. That means H8 is equal to H9. If you neglect the pump work, then you have to take the enthalpy is equal during the pumping process. Then the H8 is equal to H9. Here I am taking the value. The H8 is equal to H9. I am already take that value while calculating the mass of the fluid. Then the H8 is equal to H9. That's why we have the value of 762.6. Just incorporate these values in this equation. What is the H1 here? H1 is the 3285, I think. 3285. 3285. Just give this equation, values in this equation. 3285 minus. What is the H2 dash? H2 dash is the 3045.6. 3045.6 plus here the H3 dash. H3 is equal to 3280. 3280 minus what is the H4 dash? We are already calculated that H4 dash, that is the 3072.5. 3000 3072.5 minus, sorry, plus 1 minus, what is the M1 here? 0. Here 0.206 kg. 0.206 into, here the H4 dash is the 3072.5 minus, what is the H5 dash? Sorry, I forgot to mention here dash. You have to take the actual information. Here the H5 dash. Where is the H5 dash? We don't find the H5 dash. Yeah, here you have find that 2356.6. 2356.6. 56.6. kilojoules per kg. By what is the H1 here? H1 is the 3285 minus the H9 is equal to the H8, that is equal to the 762.6. 762.6 plus here the H3 is equal to 3280 minus H2. Here the H2 is equal to 2980. Okay. If you calculate this one, you make out the efficiency of the cycle. Just wait a second, I'm calculating that one. Okay. Here I may got the value of 0.3685. That is equal to 36 point. Sorry, 0.3683. That gives the 36.83 percentage. This is all about your problem. I have find the efficiency also. Efficiency is equal to 36.83 percentage, and the mass of the steam which is taken from the turbine is equal to 0.206 kg, and the pressure which is the steam heat is taken is 10 bar. For this, this is only just a combination cycle, reheating and regeneration combination cycle. They have a three different types of turbines is there, and there is a one heater is utilized for this. For calculating this one, you have to first find write down a draw a schematic diagram properly. Then only you have to know what is the process involved in this. Then after you have to draw a proper TS diagram. If you look into this one, the 1 to 2 is the ideal expansion process, that is the isentropic expansion process. The 1 and 2 dash is the actual expansion process. Why I am taking this is here in this problem, the efficiency of a turbine is given. That's why I'm taking the 1 to 2 dash. Then the 2 to 3 process is a reheating process. Then after the 3 to 4 is a ideal expansion, that is a isentropic expansion process. Suppose if you follow the 3 to 4 dash process, that is equal to the actual expansion process. Then after, at the fourth state, some amount of M1 mass is taken from the turbine, intermediate pressure states are. At this condition only, we have to take the pressure. Here we have given the temperature where the steam lead is taken, where the reheating process is happening. Then this is sent to the 4 dash. This is sent to the low pressure turbine at a 4 dash state. From 4 dash to 5, we have a critical expansion. Then 4 dash to 5 dash, we have a actual expansion. The condensation and pumping as well as the condensation, and again reheating, regeneration process. Then compression. Then after it is going to the boiling process. This is all about the one. For this, you have to find the mass. You have to find all the enthalpies from the Moeller chart as well as the steam tables. Some of the values are taken from the Moeller chart and some of the values are taken from the steam tables. And for this, I have to find the mass and efficiency. You have to take it down. take down of all the enthalpies values, then only we have to calculate the unknown terms. Okay. This is all about our problem. Thank you. Thank you.